All right, so we're going to continue with our investigation into how we can find distances to far objects. And remember that what we're looking at now is, specific objects that we can figure out their luminosity and how we could use those to figure out a distance to, say, a nearby galaxy or a portion in our own galaxy, etc. So we already saw that one way that we can find a standard candle is to find a nearby star cluster to which we could easily find the distance using parallax. And then we can use that then to find a distance to a star cluster that's further away. So the next method we're going to use involves something called a Cepheid variable stars. Now these are stars that actually move around on the HR diagram. These are stars that don't have a constant luminosity or a constant brightness, but they sort of pulsate, they expand and contract due to instabilities in their interior. But it turns out these are actually really useful because one particular Cepheid variable star will sort of change in a very predictable manner. So we're going to use a relationship that is known about that to figure out the distance to maybe a galaxy which contains one of these stars. So what we actually know is that for a Cepheid variable star, the period of its changing, its brightness, see, this is the brightness of a Cepheid variable star changing over time, but it's predictable. See, even though it's a weird shaped curve, it's repeating itself. So we can find the period of this variability. It turns out that for Cepheid variable stars, there's a direct relationship between the luminosity of the star and the period. It forms a straight line. So if we find the period of that star, we know its luminosity. And so here is an object that can become a standard candle, because if we know its luminosity, and then we can measure its brightness, we can figure out the distance away that star is. And if that star is found within a galaxy, then that tells us how far away the galaxy is. And so this is just another slide showing the relationship between the period and luminosity for these stars. Another standard candle is a white dwarf supernova. This is when a white dwarf gets material from its nearby star, a binary star, and it actually sort of, in a way, there's an explosion of the outer parts of the star, and that makes the star appear very, very bright. And that's what the supernova appears to. It suddenly gets much brighter. It turns out that the luminosities of white dwarf supernovas is very well known. So once again, it can be used as a standard candle, because if we see a galaxy with a white dwarf supernova within it, it can be quite easy to compare the luminosity of that white dwarf supernova and its brightness and be able to calculate the distance to the galaxy that contains it. So here are some pictures of galaxies. Above is what the galaxy looked like, and then this is when the white dwarf supernova occurs, again going from top to bottom, showing galaxies where the white dwarf supernova appears. The supernovas are sort of a transient quality. They don't last for a long time, and that's why you can see a picture of the galaxy without it as well as with it. So these become standard candles that we can use for galaxies that are quite far away. So basically what we've gone over are different methods for finding distances to galaxies that are and other objects in the sky that are different distances away. And so this has really been very handy tools to, for astronomers to figure out how far things are away. So you might be interested, this is actually related to Hubble, who was very famous. He has this law named after him, and we're going to talk about what that law means. But Hubble actually was able to show people that the galaxies, the objects that astronomers were seeing in the sky, were actually galaxies just like our own Milky Way that were much further away from us. Basically, before Hubble came along, some scientists argued that the spiral nebula that we're seeing in the sky were actually within our own Milky Way galaxies. Other astronomers felt that they were actually galaxies like the Milky Way, which were, outside of our own galaxy. So there was, a little bit of disagreement. And so what we needed to know was, well, how far away are these objects? If we know the distance, then we can figure out whether they're within our Milky Way galaxy or outside of it. So basically, Hubble focused on the Andromeda Galaxy, which is actually a galaxy that is relatively easy to see with either some binoculars or a small telescope. And he wanted to see how far away that is. And what he found was it was about, about 200 million light years away from us. So it was well outside of the Milky Way galaxy. So this was really a breakthrough because it proved that the Milky Way galaxy wasn't the only galaxy. There were, millions and millions of other galaxies, just like our own Milky Way, that we were looking at in the sky. But Hubble found out something interesting as well. As he was studying other galaxies and measuring the distance to those galaxies, he found out something quite interesting because he actually was able to show that those galaxies were all moving away from us. And the speed that they were moving away from us was related to the distance. And this is a graph showing some data and the straight line, which is what we call Hubble's law. The vertical axis is the speed of the galaxies, and the horizontal axis is the distance of the galaxies. See, the way that he was able to figure out the speed of the galaxies is when he was looking at the light coming from the galaxies, he noticed that it exhibited redshift in the spectral lines. And so remember that a redshift means that a light source is moving away from us. And remember that the amount of the shift tells us how fast it's moving away. And so basically, he found that there was a definite relationship between the distances to the galaxies and the amount of redshift, which then from that follows the speed of the galaxies. And that's where we come up with Hubble's law, which says that the velocity is equal to some constant times the distance. So whenever you have a straight line, remember that the form of the straight line is y equals mx plus b, where m is the slope of the line. We call the slope of this line Hubble's constant. And you can see that for the data, because there is a little bit of spread, we can sort of say there's a range within which the Hubble constant has to lie within. And so if we rearrange that, the distance is equal to the velocity over the Hubble constant. And so this actually becomes another way that we can measure distances to galaxies, because now that we have that line, that graph, if we measure the amount of redshift and figure out the speed that the galaxies are moving at, we can actually then, using that graph of Hubble's law, determine the distance. So this becomes one more way that we can find distance to nearby galaxies. But there's something interesting about this Hubble's law, and it really led to the idea of the Big Bang, because if all the galaxies are moving apart from each other, what does that infer about our universe? And also, can it tell us something about how old our universe is? I mean, basically, it says that if everything is moving away, then you could sort of trace that back in time to everything coming together at a certain point. And what would that time be? That age of like when they would all be coming together could be found by taking the distance over the velocity, which means it's 1 over the Hubble constant. So the Hubble constant became important not just for saying what's the slope of Hubble's law, but it also said, we say that 1 over the Hubble constant is a way for us to say how old is the universe, because it's a way for us to sort of say, if everything's expanding and moving away from each other, let's turn that back in time and figure out when everything would have come all together and been at the same point. And so again, 1 over the Hubble constant is how we could find the age of the universe, which turns out to be somewhere between 13 and 15 billion years. And so this picture here is just trying to sort of illustrate how we might be able to visualize or think about the expansion of the universe. If we take a balloon and we draw dots on it and we allow it to expand over time, notice that they move further and further apart, and the speed with which two things move apart is related to how far apart they are. So points A and D were further apart. They're going to separate more quickly than things that like A and B. This isn't exactly a perfect thing because it gives us maybe an inferior way to visualize the universe, because if we really think about how could we think about the universe, we should have to think about the fact that the universe doesn't really have an edge, and that's a problem, because I think when we imagine the universe expanding, we always think about the edge of it growing larger, but then we sort of visualize, well, what is outside of the edge of the universe? But nothing really exists outside of the universe, so that's a problem. So it's actually kind of a crazy thing to think about, and it starts to get you really thinking, but also can get you really confused quickly. And so another thing that happens is if we think about if the universe is truly expanding and light is traveling through the universe, we also have a term called the cosmological redshift, which refers to the fact that light, as it travels through this universe, this expanding universe, is actually also experiencing a redshift because it's being spread out over a larger and larger area. So this is basically concludes the material that we wanted to learn for today. How do we find distances to distant objects? And what is Hubble's law all about?